Hello, everybody. Good morning, good afternoon, and good evening. And thank you very much for joining us for this IEEE Computational Intelligence Society webinar. I am so excited today to introduce Luis Miguel Antonio, who is the Chief Technical Officer of Artificial Dynamics. This company delivers AI software solutions across domains such as retail, customer service, security, and logistics. Luis has a PhD in computer science and has also completed a postdoctoral fellowship in AI at the Franco-Mexican UMI Lab. He's got over 10 years of experience, lots of different areas in terms of computational intelligence, and has been an active publisher in IEEE Transactions on Evolutionary Computation. The talk is entitled Real-World Applications in Retail and Logistics Across Latin America. If you've got any questions, please post them in the chat, but for now, I'm going to hand over to Luis to begin the webinar, and thank you so much.
Thank you, Kelly. Well, thanks for having me here to give this talk. I will be talking about applications in real world that we have experienced here in the company. So I think I will start. First, for this part, I need to give some context. So I will talk a little bit about my company so that you know what it has to do with artificial intelligence and the cases we solve every day for clients. So the company is named Artificial Dynamics. We have several solutions that are mainly focused on solving trade problems for retail and also for logistics. We have more than 10 years of experience, and we are in different countries, mostly in Latin America. The main part, we have operations in Mexico and also in Brazil. And we have a lot of clients that have been using our solutions from different cases and also to solve different problems. But most of them are mainly for this part of the retail. So we have 5 different solutions, but in this case, I will be talking about 3 of them that are related to artificial intelligence mainly. I mean, we will see how we make use of this technology and also how is it related to this part of retail. So the first part is to give some context also about artificial intelligence. So again, nowadays we have been hearing a lot about it because of the boom and the success on natural language processing technology. But in fact, artificial intelligence is a broader field that has to do with computer science. Artificial intelligence has to do with the development of systems that tries to emulate or to give different behaviors that has to do with intelligence, mostly about reasoning, understanding, detection, and a lot of cases that we can think about. In this case, what we are going to be talking about are mainly 3 areas for artificial intelligence. One is evolutionary computation, another data science with machine learning, and also deep learning for neural networks usage. So first, to give some background about the field that we work with and also the challenges we have, I need to talk about retail. For us, these problems emerge for the necessity of solving different challenges that occurs when a client wants to consume some product in the last step of the sales chain of product development and selling. So in these cases, most of the challenges in this part are, for example, pricing, about what is the right price for each customer, depending on the zone, the kind of client, the kind of product. Also, the part of omnichannel integration. This is a lot of years, the companies have tried to give a good experience for customers in order for them to feel the same, either from buying from e-commerce or directly from the store. So it is also a challenge to give this experience to customers. Also for customer personalization, in order to bring more engagement, to bring the necessities that they have specifically for each of them, because each of us have different perspectives and needs. Other part is for the forecast of demand, since this has to do a lot with the presence of products in the stores. So it is a problem that everybody tries to solve nowadays. And also for the part of inventory and the supply chain optimization that has to do with delivering the products from the place where they were created to the place where they are going to be bought. So these are, like, in a general way, some of the problems that we face day to day with our clients. So first, I will talk about logistics for this part of the delivery of products into the stores. So the main challenges we have here has to do with route optimization, that this is about how can I deliver or how can I make visits in order to make them efficient and also to fulfill the objectives that I have of time and also restrictions. Also, there are problems in the pickup and delivery constraints, since the coordination of vehicles and also the coordination of having the product available for distribution is also a problem we face here. Also, scalability, because sometimes the demand is changing every day, so you don't have a constant behavior. Also, this has to do with the demand planning part that I mentioned before, where you need to know what is going to be the demand so that you have the resources available, not only from the product perspective, but also from the vehicles or people you need to do this operation. And well, the main problem that we solve has to do with the delivery costs that are involved in these operations. So I will talk about this. So first, I wanted to give you a perspective about the problem and also the complexity it has, so that you can understand why is it needed, the use of artificial intelligence in this case. So let's think about an optimization problem. Sometimes these problems are described as single or multi-objective problems, where you have a function that can describe a behavior or a context in the world, that you have abstract to be delivered through a function that is defining to certain variables. For example, in this case, I have a function f of x that is subject to some restrictions. I have an example here that I have a summatory of this set of x variables that are multiplied by a constant, and I'm subject to certain restrictions. This visually, you can see it on the right part of the screen. You have here the landscape of the function values that you have once you evaluate these variables. What you try to look here is to find either a maximal or global minimum or a global maximum. But in this case, we will be talking about minimization. So as you can see, one problem from each of the descriptions it can have several saddle points for local minimal or local optimal solutions that we may encounter. But this, how is it related to this part of logistics? The logistics problem, in fact, can be seen from different perspectives. One of them is through combination results that I have for the number of points that I can have from the problem. With this, I mean, I can have, for example, the necessity of delivering products to 10 points of sales. So I can have different combinations for these visits in order for this to happen. So in the computational analysis, this problem is a factorial complexity problem, where the complexity has to do with the number of points I need to work with. So either the number I had is n factorial for this part. So as you can see in this small example, I am showing you the number of combination or permutations that I have from 1 to 25 possible number of points of sales. As you can see, as I increase the number of points that I need to visit, the number of combinations starts to increase a lot. Even for a small number as 25, I have a number that I cannot even tell. So you can have an idea about what is the complexity in this part. So even though there are a lot of ways to solve this problem, there are mathematical procedures for having these solutions. Also, you have a lot of different analyses. You can tell that many of these problems, when you are talking about real world problems, have very complex behavior because for example, mathematical approaches, you need to have functions that are well behaved. However, in reality, this doesn't happen that way because the models you have and the objective functions that you define has to do with a lot of complex things that happen in the real world. In this case, for the power logistics, you can think about the different kind of routes, vehicles that you are using, the velocity you have, the kind of restrictions you can have for each road. So there are a lot of variables that are involved in this part. So there is an approach in artificial intelligence for solving this kind of problems that is named evolutionary computation. The main idea in evolutionary computation is to have solutions that represents a solution for this problem, just an instant of these several solutions that I have. And I can manage these solutions for a population. This population can have this dynamic about evolution, where I have a population that has to live in a context, has a reproduction behavior, and then it evolves through time. So with this idea, I have this here shown in 5 simple steps. First, I have this initial population that I have solutions for the context that I'm working with. In this case, it will be a logistic problem. Then I need to have a way to evaluate the solutions. These evaluations has to do with the things that I am looking to optimize or the things that I'm trying to improve. In this case, it can be the distance that I need to make for visiting these points of sales, or maybe it has to do with reducing costs, whatever I am interested in to be optimizing in this case. Once I have this evaluation, I can have a criterion for selection for my solutions. So I can tell, and I can have different operations for have selection for reproduction, for example, in order to try to look for best solutions, in order to bring better solutions when they have this reproductive behavior. And with this, I can have these crossover operators that is in this 4th step, where I can have these operations where I mix or combine these solutions, these individuals from my population, to create new solutions or new individuals. And with this, I can have this last step where I will have a selection for survival. So these survivors are going to be like the best possible solution that I have until certain point of time for the problem that I am solving. So this visually, you can see it on the right part. I have a problem where I am trying to optimize a function that has a lot of local optimums. So as you can see, there's a population that starts like distributed along all the problem landscape, but then it just starts to converge. And this conversion has to do with these operations that you are seeing here. So this is an analogy, but however, when you implement this thing, it is a kind of artificial intelligence that is non-supervised because the system starts to find solutions by itself just by setting this set of rules and to have this analogy with evolution. So how can you bring this to this first problem that I see and how it is seen to the perspective of retail, right? So for us, in order to have a system to bring dynamic routes and also logistic optimization, we need to have a core that allow our systems to bring the solutions. This core is connected to different applications, software applications, that are meant to be used by our end users and give them the leverage to create solutions for these kind of problems. Even though they may not be experts in artificial intelligence, they can have access to these solutions and bring this complex problem a good solution from just giving some click interactions in a screen. So for this, I have this one case that we have even published in a journal here. We have this research where we needed to tackle one main problem that we were having, that was about the sector creation or the clusterization of our points of sales, mainly here in Mexico. The idea was to create an algorithm that allows to create sectors that will bring for each of our operators or vehicles or drivers certain points for deliver, but maintaining certain restrictions as the time they have for work, the volume of vehicles, also the time I need to spend on each visit. Whatever thing I have as an expenditure here, I need to have it and take it in mind in order to bring one solution, to create this function that I just described before. So here you have an idea. I am showing on the right side how is the distribution in time that I have from different points of sales here from two states here in Mexico, from Hidalgo and Morelos. And you can see that you have a distribution that has points that span from just a few minutes to even hundreds of minutes. So you have a problem that has a mixture not only on the requirement of the geography that you are working, but also in the context of the operations you are spending this time with. So what we were looking was to bring scenarios as the left side scenario, where I have a very complex sectorization, where I have mixture of routes that are overlapping with each other. It is the usual way that our clients starts to work with the tools they have at the time they arrive with us. And then we managed to bring solutions as the one that I am showing on the right, where I have a more clear scenario. I have a good distribution for this, and I am fulfilling these restrictions in a way that the operation is something that can be done in that way, because even though maybe I have an idea solution, if it is not attached to the restriction that I have for operation, it may not be something that I can execute. So I have results that are well behaved, either from the theoretical perspective, but also from the operational planning and at the end for the operational execution that I will be having. So with this, you have more or less an idea about how these algorithms work, what kind of problems they solve, and how does it look for example, this case on logistics. For us, the main value that we give has to do with the implementation of logistics. How can we bring these complex algorithms to be used by people who is working day to day with delivery without the necessity to have this expertise? Also, to have a decrease in the necessity for vehicles. This has to do with not only costs, but also with reducing the pollution and all the things that are involved sometimes in vehicle utilization for delivery. Also, the reduction from distances that each of these teams has to travel in order to deliver these products. So it's something that has to do also with costs, but also with the quality of life from people, because they need to work less time in order to bring the same results. So it has a lot of implications, not only on this part from costs, but also on people that is working with this. And also this helps us to make an optimization on the way we use resources and optimize costs that at the end bring like a better operation in general for all of our clients, so that they can bring better experience for their clients also. So one of our success stories here in Mexico has to do with one company that is called Sigma Alimentos. Here we have worked with them for almost 8 years, having this logistics solution implemented with them. They have different channels here for sales. We attend mainly the traditional channel that are the small stores that you find here in Mexico. And these are around 1 million stores that we operate every week, where we are bringing this kind of solutions. And we have managed to make impact not only in savings, but also on fuel consumptions. So it is a very big deal here in Mexico, since most of the vehicles we use, they use fuel for working. So it has a lot of impact on ecology also. And also we have had the experience to bring this to reduce the time they need for planning, because before they use this kind of technology, they needed to spend almost maybe a month for each of the regions they had to plan. And after using this kind of technology, they can create a planning either from 15 to maybe 30 minutes at most. So in the worst case scenario where you have a lot of points of sales, and you can bring a lot of restrictions here. So you're not only solving like the mainly route optimization problem, but also more complex situations where you need to have restrictions in order to have a better experience for the delivery of the products. So next, I will be passed to another example of artificial intelligence usage. In this case, I will be talking about machine learning and data science for one thing that we call predictive sales. One of the main problems also in this part of retail is the part of the demand and the forecast of the demands on the stores. This is because every time that a user or a client wants to acquire a product, and he visits a store and he doesn't find the product there, or she doesn't find the product there, you have a lost sale there that you may cannot recover from. So it is an important part of all the change of all the chain of the delivery and management of production also from products that has a lot to do with demand planning. So what has to do here with artificial intelligence, and how can you see this problem, or how can you understand it from a mathematical perspective? First, we talk about prediction. The act of predict is a way to have a knowledge from future that you can have before in order to have action and prevent something to happen, right? But how can this happen if it is well known that nobody can tell the future, nobody can predict what is going to be happening? So we can have an abstraction of this problem in a mathematical perspective as a definition of a loss function, where I want to reduce some set of samples that I have, where I already know the behavior of this sample, of the output. In this case, I have this scenario of a training sample where I have a set of values, y and x, where the x values describes the y value that I will be having as a result from the combinations that you have. Maybe it can be a function, a summatory, whatever I can define to be this function. I would like to create a function that will reduce the differences between the predictions or the approximation that I have for the values and the real values that I am having from the data that I have access to. So with this, I can define this problem as a minimization problem from a loss function, where I will expect to have a value from the differences between these two sets of values. This, as complex as it sounds, has brought a lot of attention, either from the mathematical field and also from the computational perspective. What I can have here on the right side is an example of a plane where I have the real values of this plane, because I know a priori the values that I can have for the solution that I am working with. And also I have points that are like these values that I try to approximate to create a definition for this function that I already have visualized. However, this is like a benchmark problem, something that I already know, and also that I can know before how it is behave. But in the real world scenario, you cannot tell that because you are working with things that have not happened yet. So how can we be seen through the perspective of an example of this? This I have an example for a combinatorial problem where I can define this Y output through the summatory of different variables multiplied by a context, not by a constant. This constant is multiplied by the several observations that I have on my problem. And also this part tells me that I can find a way to bring certain weights to this problem in order to create an approximation from my original function. So for this, in order to simplify it, what I am trying to do is to create a function that is like an artificial function that is going to be pretty close to the original function. That is going to be creating new values for me for new cases scenario that I haven't seen yet, but I have already the necessary context and information to create this function. And this function is going to be creating new values for me. And these values are going to allow me to have predictions that are going to be approximations for future case scenarios that I will be working with. So how does this behave from the machine learning perspective? Even though from the mathematical field, they have a lot of work there for pursuing this kind of problems, again, happens the same as in the optimization problem I show for logistics. Most of the functions that I work with are not well behaved and have a lot of restrictions, and also the decision variables that I use are pretty complex sometimes because they have to do with characteristics from products, from the points of sales that I'm working with seasonality, also maybe with marketing strategies. There are a lot of behaviors that are involved in this part that are not something that is like constant or that I can model in a very good way. So for these mathematical approaches, they have a lot of difficulty managing this kind of problematics. So this is where machine learning enters in this field. What a machine learning model tries to do is to have a data that is used as an input for this. I have a set of features that describes the labels that I try to predict or to tell in this case, or maybe it can be a value that I want to predict. And I can build a model from there. So this model can be seen as this function that I mentioned that is like an artificial model function that I can use in order to bring new labels or new values, new data from these new features, and use this new model in order to create new knowledge. So how this can be seen, because there are a lot of algorithms that works in this way, but most of them have like the following idea that I present here on the right side of the screen. Here, what I have is that I need to have a train set that is this set of instances from my data that I will be using for training this model. And most of this training is going to be to create weights or variables that are going to be helping me to model like this behavior for my function that I want to have in order to have this new behavior that is going to be very close to the original behavior that I already seen from the data. And also from this data, I will create a test set in order to validate the information and to validate the behavior of the model. So in sense, it's like a posting machine where I have several steps of improvement to this set of information, and I will create a model from the training set, evaluate it, and then see where I did wrong. What are the predictions that are not well behaved? Take these new predictions and try again to create a new model or to improve the current model that I have so that I can have an improved model at the end that is going to be pretty close to the original model that I am trying to emulate or to create. So with this idea, what I'm having here is a system that allows me to create a model. And this model is created from certain parameters by the use of heuristics and also from certain steps that bring me a way to create solutions for these problems that even though are not exact as the original model, you can have a good approximation that can give you some insights in order to act for future scenarios. So this is something that is called supervised because you need information for this in order to work. However, this is not the only kind of model that you need in order to work with data science and also with these scenarios for demand prediction and for other aspects that I will be talking about in a minute. You also need another kind of algorithms where you may don't have the necessary information, or maybe you don't need it in that way. So these are kind of algorithms that are known as unsupervised machine learning algorithms, where the insights or the results emerge from the behavior of the algorithm. It is something more near to the first kind of algorithm that I talk about, that are these evolutionary computation algorithms. But in this case, I have another kind that is meant to be for clusterization. This clusterization problem has to do with the segmentation of solutions in order to bring a classification for them, but from something that brings out from the context, not by telling by example, but letting the system to learn by itself. So here I'm showing you like the most known algorithm that we have in the state of the art, that is known as the K-means algorithm, where I use this idea of centroids, where I have information from these centroids and the set of points that I have and that I am evaluating on this pursuit of clusterization. And I have just 4 simple steps. I first need to define these centroids. They have to be in the region that I am working with. I will be creating associations between these centroids with the current values that I have. And I will be improving these centroids for each new classification that I have. So as you can see in this third step, I am going to create new centers that are going to be bringing a new mean from the current solution that I have. So with this, what I am trying to do is what you can see on the right side of the screen, that is to segment the solutions and to have a clear perspective of which kind of groups you can have for these solutions. And this can be whatever you want, as long as they are numbers, and they can be, or they can come from different perspectives. For example, from our case, where we talk about demand from products, we use this mainly for clients filtration, so that we can have a classification from clients so that I can know their behavior. I can try to segment the behavior to take decisions among several clients, and with this have a better strategy that is a more tailor-made strategy that is going to be more successful for each kind of client, instead of trying to have a general strategy that mainly cannot work for everybody because every one of us is different. So you need to have a strategy that is different and that allows you to create more value for the client that you are working with. So how can I connect all this, and how is this related to data science? From the perspective of data science, you need to talk about not only machine learning models or this part of model creation, but you have to talk about also data. How can you manage data, and how are you going to be working with this data? Because at the end, even though you have these complex models, they depend on data in order to be created, and also you depend on this in order to have new results. So for the part of data science, you need to also be engaged in data engineering. So for this part, I have here like this kind of pipeline where I am showing you what is like the transformations that data suffers, and also the necessities or the steps they solve on each of these parts, right? So at first, you need to have the fundamental data, or the first basic part of the analysis, in order to have a problem definition and a strategy. So what you have here is a big source of data from different domains and from different sources that you need to be working with, and that you need to have a context about it. So most of this has to do with exploratory data analysis, with data extraction, transformation, and also consumption, and to have this data loaded already in certain kind of repository. Then you can learn from this data. That this learning comes from this part of this modeling that I mentioned. When you want to have a creation of a model or an archetype that is going to allow you to learn from this data and from new data that you are going to be having on next steps or on future operations from the strategy you are working with. Then you need to have this training from this data so that you can have a model selection so that you have the right model in order to be working with this data and to bring this value and to have these different results that you are going to be used. So you have a more refined data, focus on this model design, and also thinking about the results you want to have. Either if you want to talk about predictions from demand, or you want to talk about inventory, and also if you want to talk about client segmentation, whatever you want to work with, you need this data in order to have like this more focused information in order to have these new models. And then after you have already this model, you need to talk about model deployment, where you are going to be have this model using on production, and you will be operating this in order to bring information as input, this new information, and as an output, these new insights that you will be using for giving results or strategies to clients, right? And at the end, you will be having this model monitoring from the output so that you need to be sure that the model you deploy is still something that is useful, that is having the results you want, because these kind of models are like on constant learning. So you need to be having them constantly trained. And also you need to check if the objective they were created to is still fulfilled, because some of these algorithms tend to decrease their performance as the time goes by. So you need to update this data for new trends, because sometimes something happens that is new for the model. So you need to inform the model in order to have all this context and to be still something that is good for you, that is bringing good solutions, and that is going to create good strategies that you need. So I already talked about like this more technical and more artificial intelligence oriented, but how it is used at the end, this data science for real world applications. Well, first, you can have different strategies depending on which layer you are working with. But at the end, we can resume this in these 6 points, at least as we use it right now. First is from a perspective for numerical distribution, where this you want to analyze where is the product and which of the clients you already have is the product already existed there, in order to have a knowledge to have what is the opportunity you still have for this product to be entering to new clients. So for this, you use this knowledge and all the history you have from data in order to bring this numerical distribution so that you can have at different layers the information necessary for bringing these suggestions for this new product to enter to new markets, to new channels, or to new points of sales, whatever you need on each of these layers. Also, you can have this information in order to get to know the purchase behavior. So you can have this analysis from the customer perspective to have the buying patterns they have, so that you can tell what is the way the product is going to be behaving through each of the stores, through each of the seasons you have in time, and also through different regions, or depending on each of the channels you are working with. So with this, you can have an impact that eliminates the excess of inventory from different parts of different channels, so that with this knowledge, you can tell before where do you need product, and maybe where do you have more product than the one you need from the stores. So this has to do a lot with costs of operation, or having these products on the stores where you may need it in another stores that is being asked for these products and you don't have them, right? There's another layer also that we work with, that is this basket analysis or assortment mix, that has to do with the composition of the catalog of products that you have available on stores. This has to do also with the kind of products that the clients buy and which kind of mixture they need, either from the kind of customer you have or for the kind of region that you are working with. So most of these are like basket analysis algorithms that use information from the mix of products that were bought together, and how can you tell for future purchases, how can this behave, and you can have also a strategy from them. The other part is customer classification, where I already talked about this, but you can have this knowledge in order to create a strategy, to have a more focus-oriented strategy for each of the clusters you define. And also you can have a knowledge about which kind of behaviors work well for each kind of client, because different clients behave different depending on the acquisition capacity they have, on the kind of products they can buy, and also by the geographical context they have, because maybe the place where they are have different kinds of clients. So all this has to do with this customer classification, so that you can give a more oriented strategy and give even insights as new product suggestions, and also to have these kinds of preference in order to give like context for clients that you already have, but that can give more to you in terms of sales, because you can see other clients that are working better with the same context and the same features, but they have this opportunity there. So this can be brought through this customer classification, through clusterization. So this give us also these points of sales potential, where you can find a way to work with the replenishment. You can tell what is the potential of each point of sale by knowing how many new products it can have, and also in terms of volume, how much volume you can increase according to the context you have found from the data. So this gives you an action and also a plan from a planning perspective, in order to have a better strategy for distribution also for these products. And at the end, all of this is used to create something that we call suggested order, that is this artificial intelligence algorithm that creates a plan for each of the points of sales automatically, only using history from the data. You can use these different layers of artificial intelligence and also from data science operation in order to create a very specific plan to tell for each point of sale which product and in which quantity you need to deliver, so that you can have a healthy inventory on the points of sales, and also happy customers that can acquire the products as they need it, right? So in this, what we see as value from this solution is an advanced sales forecasting model that is based on data science, that allow me to plan great volumes of data and improve accuracy for this, so that my planification is good and I have no lack of products in some places, and also I don't have overstock implementations on some others. Also, this give me an improvement on inventory optimization and a great mix accuracy, so that I know which kind of products work well on each case. And this ends in an incremental of sales that works in upselling and cross-selling scenarios. So you can have this increase in sales that every of our clients are looking for this. And also you can also improve on efficiency, reducing costs of stock operation by bringing down the overstock availability and the understock cases also that you have on different scenarios. So this is the way that we work with. Here, talking about another success case, we have been working with British American Tobacco. This company has been using our solution in order to make planifications for all the strategies they have for their products, and also for an objective-oriented strategy, where they need to have a good planning for the objectives they have each year in order to bring the sales to the state that they want. So we work with around 250,000 points of sales where we plan every week. And for this, we have managed to create reductions in lost sales by having the availability of products on each of the different channels they sell. Also, we have increased the product stabilization. This means that you can have the products with a good behavior each week. You don't have like this kind of bad behavior where sometimes you sell units, sometimes you don't. You need to have an stabilization so that you can plan better. And with this, you can have an increase in sales and specific in these objectives they have so that you can have a better performance for all the planning they have from the production stage to the part of the delivery and the sales and the way they can plan this and bring this all together. So these are cases that I brought to you in order for you to understand this part. And at the end, I won't enter to so much detail on this last solution because of the time, but I wanted to also talk about a case for the use of deep learning and neural networks for video analysis. In this case, we managed to create a solution that uses video in order to identify customer behavior, or what we call like as the shopper path analysis from certain scenario and certain context. What we do is to analyze video, to process this video, to use deep learning in order to make detection and classification of objects inside images. Most of the cases that we work with is about detection and classification from people in stores or in malls. And this allows us to bring information to take better decisions, either from the perspective of knowing where the customers are most of the time, which path do they take, and how long do they take on each of the interest zones that I am analyzing. And this gives me different tools in order to implement marketing strategies, maybe, or also to bring pricing for different areas. If I am talking about a mall, for example, so that I can tell how much valuable is a zone depending on how much traffic for people does this place have, right? So here, what we do is to use what is best known as computer vision in order to bring like this value for our clients, to have this mapping of visited locations from zones of interest. Also, this interest analysis in order to see if maybe customers are engaged or are looking to certain products in malls. Also, this route monitoring so that I know where the shopper walks by or what is like the route it takes. Also, the peak hour identification so that as I am measuring the number of people that is entering to a mall or to a shop, I can tell in which hours you have the most of the visits and where do you need more like either help from people from attending these clients or maybe some strategy that you want to implement. You can tell what is the best time in order to implement it so that you can have this planification from strategy and actions using this data. Again, you can use data science and bring new insights from the data that you generate through deep learning. And at the end, you can have like these better insights for clients in order to create actions. This must be used for trade marketing, but also has a lot of other applications for different perspectives, but most of them also implemented for the retail programs. So in this case, we have this success case here in Mexico City, where we are working with 11 malls here in Mexico City. What we are tracking every day, 24/7, all the traffic of the people that is attending this shopping mall. Here, we have managed to make use of cloud computing and GPU in order to have this implementation. And this has brought a lot of insights for us in order to use this big data information to bring not only like the history information that I already have and the analysis in order to bring like these valuable scenarios, but I can also use this information again to create future scenarios and to know which future strategies I can use. So again, this is everything for my part. thank you very much for having me on this talk.
Thank you so much. And for anybody who's listening, I'm going to come to your questions now, but I think that was really good to see the complexity of a number of students maybe just doing projects in one area, but this is showing the power of combining a number of different algorithms together and to get that insight from the data. So what we're going to do, we're going to leave Lewis's contact details on the webinar at this moment in time. I'm going to go to the chat. The first question came very early on when you just started, and it was by Usman, and he was asking a question with regards to the number. He says, what is the number in complexity here? And I think it was about one of your very first slides on complexity, but he's just asked for that clarification.
Okay, well, about the complexity, it depends on the number of points that you are working with. But if you talk about, as in computer science, we talk about big O notation, that is like the worst case scenario. The number depends on the number of instances that you want to optimize. In this case, for us, for example, we are working, most of the scenarios, if I talk about a region, are about 20,000 points of sales that I am optimizing at the same time. But this, again, as you talk about the whole problem, is about millions of points of sales. So you need to compute the factorial of these numbers in order to know what will be like the whole number of combinations. However, you don't need to know them, because when you use this kind of technology, you can have like this exploration from different solutions and to bring a pretty near, if not almost the nearest maximum optimal solution for these cases. So, I mean, the computation depends on each of the cases that you are implementing this technology.
Okay, hope that answers that question. And the next one is from Jayant from India, and it is, how do you balance the trade-off between AI model complexity and interpretability when deploying solutions in operational retail environments?
Okay, that's a great question. In fact, in order for this to be successful on real world implementations, you have to take into account the perspective from client and from business. So most of the time, what we do is to generate solutions that make sense at the business level, so that I don't know, not only look at maybe the measurement of my key performance indicators, or maybe the evaluation function that I am using in order to see if the model is good, but I also need to take a look if this makes sense in terms of business. For example, even though maybe I have an error of almost zero for one predictive model, if the suggestions that I am having are not well behaved for the case scenario that I am working with, I can tell a wrong suggestion. For example, if maybe I have a store that only buy I don't know, from hundreds of products to thousands, but maybe I am suggesting millions, I am making a huge error that is going to be something that my final clients are not going to be accepting, because the criterion they have from the business perspective is different. So the balance there have to do with having knowledge from people, from data science, data scientists, and also from business, because we use a lot of knowledge from this part, from our clients also, in order to together measure the quality of the solutions. So at the end, either for clusterization, for prediction, for basket analysis, all the results are like supervised together in a certain way, and we can reparameterize these algorithms in terms of the feedback that we have from our clients. So I think that's the way we balance. We need to take into account the business model perspective and also the technical part from data science.
Wow, that was a good answer. Ooh. The next question is from Catherine, And this is a good one. I'm interested in this one as well. When you use evolutionary algorithms to solve logistical problems, how do you commonly handle the constraints?
Okay, well, most of these constraints are part of the problem definition. What we try to do is to bring these constraints either in two ways. To bring this as a multi-objective problem where I can have these different restrictions also modulated as an objective function, and I can work with this in a multi-objective scenario so that I don't have a single solution, but several solutions that are a trade-off among them. This means that you cannot tell which one is better, but you have different cases where you can evaluate them from different indicators. And the other way we do this is to have like different layers. For example, first, I tackle the sectorization problem. And then there, I don't care so much about the restrictions from time window, for example. But then after I solve this problem, and first, when I solve it, I try to make an approximation of the sequence of the visits, but it is not like the end result. I pass to a next layer where I optimize the solution. And then there I take a look at these new restrictions, but only from the sequence perspective for the order where I have for the visits. And there I will tackle the minimization of the distance and also these restrictions that I might have for time window. So in general, it has to do of how you model these problems. That's the key of the success. How do you model this in order to program it in a computational language, in a programming language, and having like these success cases. Also, another key factor is the parameterization of the algorithm, because if it is not well parameterized, you tend to fall in local optimums. So that has a lot of things also, has a lot to do with the results you have to have a good parameterization for each of the algorithms you are using.
Very much. That was really interesting. So we've got two questions, so I'm going to get them in. The next one is, have you explored real-time AI-driven decision-making systems, and how do you handle latency or scalability issues in such cases?
Okay, that's also a good question. Because of the time, I focus on most the theoretical part, but there is a very important component here that is the software engineering part that we didn't talk about. But in this case, in order to have this as something available, you need to make use of up-to-date technology. Mostly it has to do with real-time processing. There are a lot of open frameworks there that you can use. For example, we make use a lot of Kafka, for example, technology. That is an open source technology that you can use for Fluxus data scenarios. And also we use also a lot of containerization, in this case Docker, in order to encapsulate solutions and make it possible to deliver or deploy these solutions on different servers without the necessity of have each implementation manually, but just to replicate the encapsulation you have. And you have to work also with different layers here. Talk about CI/CD, DevOps, and also with modularizations of code and development. But most of these have to do also with cloud computation. We make use of a lot of cloud providers in order to have this availability and resiliency, because this is another big challenge to have like these operations from infrastructure. So at the end, is this connection between infrastructure, software engineering, and artificial intelligence all together in order to bring solutions that are something that gives you good latency, good availability, and good results.
Thank you for that answer. The last question, I know we're slightly over, so I think it's from Michael, but I think an interesting one is, do you specifically use any open source software?
Yes, in fact, most of the things you saw are something proprietary from us, because most of the things we managed to bring them from open source to be tailor-made by us with research and development. So most of the things I talk about has to do with using frameworks, open source frameworks, for example, Angular for web development, Kotlin for mobile development, Spring or Flask or FastAPI with Python for services, and so on. So most of the things we create these programs, we work with Python, with Java, with R, with Node, talking about some of the languages we manage in order to create these different layers. Because here we talk about the core, but you need to be aware that in order to bring these solutions, you need to make use of other layers, mostly from the application layer, in order to have this final solution be used by people who is not so technical, but that can have access to this through web applications or to mobile applications. So yes, we mostly use open source for most of the applications we have here.
That's great. Well, thank you very, very much, Lewis, for that really, really great webinar. Thank you to our attendees as well for the great questions. We are just over time now, but before you leave, finally, the contact details for Lewis are on the screen. I hope you managed to grab those and follow what the company artificialdynamics.ai is doing. And before you leave, we just want to tell you about the next webinar that's on. There is a QR code on the screen, or you can actually go onto LinkedIn and follow the Computational Intelligence Society for more webinars. And this one's on simulation-based AI with large language models by Professor Simon Lucas, and that will be on Friday the 13th of June. So again, please feel free to log on and register to join that one. We've got a lot more coming up as well. So without further ado, I would like to say one last huge thank you for Lewis for sharing those insights and those really, really interesting problems. It was pretty good. And I may send you a message about that later via LinkedIn. Is that okay?
Yes, thank you so much for having us.
Absolutely fantastic. Oh, okay, everybody. Thank you very much for attending, and we can now end the webinar now. And I'd also like to say thank you to Tom, who's an IEEE Director for Computational Intelligence Society, for joining us. So thank you.
Thank you.